So for the given circuit, I want to find Norton's equivalent circuit for terminal A and B. And first I will find Norton's, in order to do that I will find Norton's current first, and in the next video I will find the Norton's resistance, because this problem is a bit involved and I will do it in two videos. So for the first, to find Norton's equivalent, Norton's current for terminal AB, I have to short circuit this terminal and I have to find current I short circuit, which is Norton's current. Now in order to do that, I notice when I look at this circuit, there is this one is a voltage drop across 3 ohms resistance, and this voltage drop is acting as a controlled voltage for this voltage controlled current source. So here there is a fixed voltage source, an independent voltage source with a series resistance, and I could think of converting it into a current source and a parallel resistance, and then these two resistance would come in parallel. They could be combined and then reconverted into a current voltage source and series resistance, and that way I would get just one. I could get rid of this resistance basically, which I have done in some of the problems, but in this one I can do that because this terminal I cannot touch. This one is a control voltage for this one. So I will try applying some other method. I will try seeing if I can write the node equations here. So let's say this node is of 0 voltage, this is ground, then this point is ground as well, because this is connected by a short circuit, and there is from here to this point, this node, there's a rise of V0, so the voltage here is V0. So if I look at this node, which is node A, I see that the current going away is I short circuit here, and this one is going away in the other direction, so that is minus 0.25 V0, which is the control dependent current. And then here the other current, which is through 2 ohms, if I say in this direction, that will be V0 over 2, because the resistance here is 2 and the voltage here is 0. So V0 minus 0 divided by 2 is the current in this direction. So that's there. So I can see that I short circuit is, this is 0.5, so 0.25 V0. Here I get one equation, a relationship between V0 and I short circuit. So that's there. Now I will write the nodal equations, the basically junction equation for this node V0. So I will write the Kirchhoff's current law for this equation. So V0 minus this current can be written as, so I will write the currents as away in the left hand side, away current, so away from the node. So V0 minus 18 over 6 is this current, then the downwards will be V0 over 3, then I have V0 over 2, which is this current as before, and on the right hand side I am writing the entering current. So these currents are leaving current from the node, and this is entering current, which is 0.25 V0. So I can multiply both sides by, I will multiply by 6, so that will be V0 minus 18 plus 2 V0 plus 3 V0, and then it will become 1.5 V0, 1.5 V0, like that. So if I rearrange these ones, V0 in one side, I get 4.5 V0 is equal to 18, which gives me V0 is equal to 4. 18 divided by 4.5 is 4 volts. So that's that. So what I actually need to find I short circuit, and I have an equation is as 0.25 is equal to I short circuit, which is I Norton, is equal to 0.25 times V0. So 0.25 times V0 I have now 4, so that's just 1 amps. So that is the Norton's current for this circuit. So I will try to find the Norton's resistance in the next video, because I don't want to make this video too long.